Okay, so now what we are saying is, whenever we try to deform anything, we need to spend work. When we do some work on the object, then deformation happens. Now, this spent work is actually getting stored inside that object. So, what the work we are spending, that get stored inside that object. Now, when we remove that straining load, then because of this stored strain energy, this object bounce back or tries to negate the deformation and tries to get back to its previous shape and size. Now, so actually we are spending work, that work is getting stored inside that object in the form of strain energy. Now when we are removing the external effort or external load, then because of this strain energy get spent by that object, and by spending this stored strain energy, the object tries to get back to its previous shape and size. Now, so when we draw the load versus deformation or load versus extension or load versus compression curve before elastic limit, the curve will be straight line. The curve will be straight line. Now it depends, because while we are talking about axial loads, in such cases there are three different ways we can apply the load. So we will talk about strain energy due to tension or compression. Tension and compression means on axial load. Now this tension and compression both are axial load. So what happens, the work spent to cause deformation is stored inside the object which is getting deformed upon which work is being done. Okay, now so the work done is equal to the stored energy. Now then, if we go back, I hope the video paused. Give me a moment. Okay, I hope this is okay now. So now what we are trying to say is, if we draw the stress strain curve, in previous case we have seen it just look like this. Okay, now when we do the work is getting stored. So this area bounded by this stress strain curve this area is actually the measure of strain energy. So this area bounded by the stress strain curve is the measure of strain energy. Now we will discuss part by part. So we will try to draw this figure a little bigger way so that our understanding becomes much easy. This is the curve. If we can remember the different points, up to this point it is proportionality limit, this point elastic limit, this highest section is yield point, this is another yield point, this is ultimate stress, this is breaking point. So we are increasing the stress, and stress goes on increasing and the material goes on deformation. Okay, so at this breaking point the material breaks, so the total energy absorbed is the total stored strain energy that can be stored. So total work to break this material is stored by this shaded area. Now if we talk about strain energy up to the elastic limit, okay, we will talk about only this much area. Okay, so before up to elastic limit, the strain energy that is getting stored inside that object, we have started from zero stress, we are reaching up to elastic limit. Okay, in this region the applied or the spent work will be equal to the stored energy. Now this stored energy at any level before elastic limit or up to elastic limit will be called resilience. That will be called resilience. So what is it? Total strain energy stored in a body when the loading is up to.
Sir, video is paused.
Okay, let me check. It is okay now, I think.
Yes, sir.
Yeah, this happens due to momentarily network disconnection. It automatically get fixed by a few seconds. So if any problem occurs, you inform me and I will try to solve it. Okay, so now resilience means the total strain energy stored in a body when the loading is up to elastic limit. So is the definition clear? What is resilience? Up to if the loading is up to elastic limit, then the work done will be equal to the stored strain energy, and that measure of strain energy will be called resilience. So the maximum value of resilience will be at elastic limit. So max value of resilience will be at elastic limit, and that value will be called proof resilience. This will be called proof resilience. Now, this proof resilience per unit volume will be called modulus of resilience. It is actually ratio of proof resilience by volume of the body. Okay, so this is modulus of resilience. Now we will learn the expression for strain energy in a body when the load is applied gradually. There are three ways we can apply load. One is gradually, very slowly increasing from zero. The second is a suddenly, and third in terms of impact. We will learn one by one. Let us see how much we can cover. So first we will learn load, axial load applied gradually. Okay, then what happens? If we draw the load versus extension graph, initially by Hooke's law we can get that this curve up to elastic limit will be linear. We are not talking about slope. Okay, the curve will be linear. The much ductile the material will be, the lesser the slope will be. Now, if this is load and this is extension, and this is how the curve will increase. So in such case, we know that the work done by the load is the area of load versus extension curve. Work done will be equal to area bound by load versus extension curve. So in that case, suppose if the loading is up to this level and the relative extension is up to this level, so extension is denoted by x and the loading is denoted by p. So then the area bounded by this curve will be this much when the loading is under elastic limit. So in that case, the work done will be area of this triangle. So if we name them O, say this is M, this is N. So in that case, the area will be half into ON into MN, or you can say half into P into X. Now why this happens? You can discuss it in different way, like when the load is increasing gradually from 0 to P very slowly, then the average load acting on this case will be 0 plus P by 2, and the extension will be x. So again the work done can be equal to P by 2 into x, which is similar to this area. Okay, this is known that work done is equal to load into extension. So that in this way also we can prove that work done is P by 2 into x in case of gradual load, or we can get from this curve also the area of the curve can be found out half into P into x while the load is below elastic limit. Now again we can write that this load P is equal to stress induced into area, and the extension x can be written as strain into length, that will be extension. So strain can be again written as stress by E, sigma by E, where E is elastic modulus, into the length initially if was capital L. So now we have get two values, P, value of P and value of X. Now if we put these values in this equation, then what we get, half into sigma into A. This is the value of stress. Now if we put the value of X or extension, it is sigma by E into L. So we can write half into sigma square by E into A into L. So looking at the equation, this A into L is the volume of that object. So it becomes half into sigma square by E into V. So it becomes half into sigma square E into V. So this becomes the expression for strain energy that is getting stored inside an object. Okay, now we will go for the next topic. So looking at the equation, we can say, looking at the equation, we, looking at this equation, we can say that at elastic limit, the strain energy that is called modulus, sorry, that is called proof resilience. Okay, that we have discussed earlier. So proof resilience value will be from here half into sigma star square by E into V, where this sigma star means stress at elastic limit. Now then modulus of resilience.
Sir, the
Yeah,
video is
yeah,
paused, I
yeah.
suppose.
I have found out. Yeah, I am on it. I think it came back. Yeah. Okay. So now the modulus of resilience will be the value of proof resilience by the volume. Volume is simply can be written as V. So as a result, we will get half into sigma square by E, because V and V will be cancelled out. That is the value of modulus of resilience. Sorry. Okay. So now we'll go for the next topic. Oh,
Sir, please can you show the formula once again?
yeah. Sure. Let me have a glass of water. I'll take 2 minutes of time. Okay. The next topic is the load strain, the expression of strain energy when the load is applied suddenly. So what is the difference? In the previous case, the load was increased gradually from 0 to P. That means very slowly the load was increased. Now, sudden load means when the deformation has been occurred under constant load. So if deformation occurred in say 2 seconds or say 3 seconds, in that particular time the load was constant and the value of the load was P. So that P load was constant throughout the time of deformation. So while the body was getting deformed, the load was constant. It started with P, ended with P. That is called sudden load. So in case of sudden load, the work done will be equal to load into extension. Now, as P is constant load applied throughout the time, an extension made is X. So the work done will be P into X. Now, the maximum strain energy that is stored up to elastic limit in a body will be given as by the expression U equal to sigma square by 2E into V, or simply sigma square by 2E into A into L. That is what we have already found out. Now, this work done is equal to this max strain energy at elastic limit. So, now this at elastic limit, the max strain energy will be equal to the work done at elastic limit. So, let me write at elastic limit, sorry, this is limit. At elastic limit, the work done, that will be P into X, where the X is deformation up to elastic limit, that will be equal to the expression of the strain energy sigma square by 2E into A into L. Now we will cancelling this sigma into L by E from both sides. Finally we will get, we will write cancelling. Okay, this is equal to, let me write the expression here. Putting this value of X what we have got in our previous topic here. We have got x equal to, sorry, my video got stopped. Let me fix it. Okay, so now it got back. Oh, again it got crashed. Okay, so so here we have found out the value of x is sigma by E into L. We will put this value here, P into sigma by E into L, that is equal to sigma square by 2E into A into L. Now from here we can write that P is equal to sigma into A by 2, or from here also we can write that sigma is equal to 2 into P by A. Now look at the value. When the load is sudden, we can see that the value of stress is twice. When the load is sudden, value of stress becomes twice with compared to gradually applied load. In previous case, the load was, sigma was just simply P by A in case of gradual load, but in case of sudden load, the difference is the induced stress is twice of that stress which has been occur at gradually applied load. So this is where we will get the difference. Now after we get the value of stress, after we get the value of induced stress, then this extension x and strain energy can be found out. We will, again the video got stopped. My software getting crashed, I don't know why. Probably they need to update or something. Yeah, there is an update available. However, after the today's class, I will update it. So let me bear with me for the last 5 minutes. After the class, I will update the software, but let me finish the class first. Okay. So okay. Now we will solve the scenario with a problem, and we will do it very quickly as we have very less time left today. Whatever software you use in every week, probably every day they are giving an update. It is very tiresome job to update everything. So let
So,
us, yes,
so in case of this certain loading,
yeah,
the graph representing this load versus extension will be a line parallel to the extension.
yes, right. It will be horizontal line above the stress value from the horizontal line,
Okay, okay.
like this. Okay, good question that was. So from these questions, I can understand whether the concept is getting built up or not. It is on a positive note. So now we will talk about a problem. A tensile load of 60 kilonewton is gradually applied to a circular bar of 4 centimeter diameter, 5 meter long. Okay, let me draw this. This is a circular bar under tensile loading. Gradually applied load value is 60 kilonewton, and this diameter is given. That means cross section is also can be found out, pi by 4 into 4 centimeter given, so that means we have to convert it into millimeter. That will be 40 pi by 4 into 40 square. Okay, that will be the cross sectional area. Length of the bar is given 5 meter, so we will convert it into mm. This is mm square, this is in kilonewton. We will convert it into newton. 60 into 1000 newton, and elastic modulus is given 2 into 10 to the power 5 newton per millimeter square. That is the given data. Okay, we will write it up. Now the problem is transparent to us. We have to find out the stretch in the rod, that means x. We need to find out the stress in the rod, and number 3, the strain energy absorbed, what is u. These 3 things are to be find out. Okay, so before we start, we know u equal to sigma square by 2e into v. We need volume, so from here we can find out volume, a into l, which will be pi by 4 into 400, sorry, into 40 square into 5000 mm cube. I will make it short. 2 into 10 to the power 6 pi mm square. Okay, now Young's modulus is also given. So first we will find out the stress. Stress is equal to load by area. Load by area means 60,000 by area is 400 pi. Solving it, we will get 47.746. These are very easy things. I am not getting into details. Now we have to find out the stretch x. The value of stretch is given by the formula we have already found out, sigma by E into L. That will be equal to stress value we have just found out by E value is 2 into 10 to the power 5 into L 5000. X can be found out as 1.19 millimeter, and U is equal to sigma square by 2E into V. Now let us find out what we can get by 2 into E into V is 2 into 10 to the power 6 pi. Finally, we will get 35810 Newton mm or 35.81 Newton meter. Okay. Now, this was very easy. We just put the formulas, put the value on the formulas, and we get the answer. Now we will discuss if the load (60 kilonewton) applied suddenly, then find out maximum instantaneous stress induced, instantaneous give me 2 more minutes, elongation, and strain energy absorbed. This is what we have to find out. So now we know that when the load is sudden, the stress will be 2 into P by A. That is what we have found out. So 2 into 60,000 by 400 pi, which will be twice of the previous stress value. So 95 into 493 Newton per millimeter square. We put this stress on the formula of stretch. Again it got stuck. Okay, so now the formula of X is well known, sigma by E into L. Put this new value of stress here, 95.493 by E is 2 into 10 to the power 5 into length 5000. We get 2.38 millimeter, just twice as that of previous. Now the strain energy is sigma square by 2E into V. Putting the values, 95.493 square by 2 into 10 to the power 5 into V is 2 into 10 to the power 6 pi. Finally we get 143238 Newton millimeter. So finally we will get 143.238 Newton meter. So actually the thing is, the stress is getting doubled, and we put this value of stress on value of this formula of stretch and this stored energy. Okay, so this is how we will solve the problem. Any questions? Otherwise we will stop here. Time is also up. No questions? Then we will continue on the next class. Thank you everyone for being patient. We'll meet you tomorrow.